Yo, Flows, I hope you're all doing well. Thank you all for coming. It's good to see you guys. So tonight I think it's going to be interesting. By the way, I'm on the Generator tonight, so this stream is sponsored by Generator, but it's good to see everybody here. Thank you all for coming. Yeah, we're going to be going through some thermodynamics tonight. I was hoping I would get the presentation much better, but I've got through the little bits, details, just so the main thing, so people can understand it in a very simple way. Obviously, I'll do a part 2 sometime with a bit more, how can I say, what's the word? Updated.
Detail?
Yeah, more detailed physics. I'll say it will be a level up. This is more of just an introduction into thermodynamics, I'll say. But it does give the gist of why space is fake and why thermodynamics destroys the globe. But yeah, it's good to see you. We got Michael Kahn, Peter Cruikshank, and Jeff Conkle in. How are you guys doing?
Hello. Good, all good.
It's good to see you guys.
Usual, there's flat and Jesus still loves us.
Amen. Exactly.
Amen.
So we got our votes going on. 14 votes already. The law of entropy. This is just, obviously there is wrong answers, but I mean, I can't expect everybody to know this, so it's just to see more or less where we are on par, to see if anybody actually knows, because if you don't know the second law is thermodynamics, then where have you been? Hiding under a rock. We do have 7% voted yes for the first law. 80% got the second law correct. Third law, no one voted, so good on you guys. Fourth law, 13% people. So the people that voted first law and fourth law, sorry to say, you guys got it wrong. It's the second law. It's the law of entropy. And then everybody in chat, just want to say hi to everybody. Jeff Conkle, good to see you, mate. Alan Norstrand, Professor Harvester, Awesome Lawson Clips, hello. Triple X, thank you for coming. Iron FE, thank you for coming. YouTube, hello. Gary Wybenga, good to see you. And Jeff Gassett. So what are you guys in the panel? What are your guys knowledge on thermodynamics? What would you rate it though?
Mine about 2.
I'm sure it's better than that.
Yeah, probably.
I would say a globe is more
2.
on 2. You guys are at least a 5 or a 6. Come on. If you understand that gas expands, then you already know you're on a level 5. And you need containment.
Yeah. No comment.
But it's good to see you guys. Thank you guys for coming. See, I'm just going to get my video up as well, because I did also make a quick little video.
I know things go from order to chaos. I know it doesn't go the other way around. You know what I mean? You can't go back from chaos back to order. When it comes to entropy.
Yeah,
whenever an object in motion comes into contact with another object.
Reversibility.
Yeah.
It says clown.
I got even Professor Dave up just for the globies.
Not a Professor Dave.
Not a Professor Dave. So we'll
Again,
start.
that would fail in this.
So this is about 14 minutes long, this video, and I just cut segments out just to see if people listen. So I'm gonna let it play through, and then we let people watch it, and then we can ask questions based on this, and then I'll give the presentation. Does that sound fine to you guys?
Fair enough.
That's good.
What, are you asking us questions?
Yeah, why not? It's like just little general knowledge on what's being presented here. It's actually very easy.
Okay.
That means I've got to pay attention.
Don't you pay attention on my streams?
No, I'm always in a dream world.
Okay, let's do this.
Whenever an object in motion comes into contact with another object, we can call this event a collision. And this concept applies to balls on a pool table just as it does to tiny molecules. In any collision, there must be a conservation of linear momentum. But this can manifest itself in different ways depending on the type of collision that is occurring, elastic collisions. These resemble collisions between balls on a pool table, where the objects involved remain separate after the collision occurs. With elastic collisions, total kinetic energy will be conserved, as well as the total momentum of the system, so the objects will bounce off of one another with no energy lost whatsoever as a result of the collision. We approximate collisions between atoms and molecules as being elastic when we refer to an ideal gas, just the way we do with billiard balls.
The particles of gas, either molecules or atoms, are never static and move randomly in different directions, taking straight line paths. This continuous random movement of gas molecules in different directions is called Brownian movement. The individual gas molecules always travel in straight lines with different and constant velocities. The molecules collide with each other and also collide with the walls of the container. The pressure exerted by the gas is developed due to collision of gas molecules with the walls of the container. Further, it may be noted that the gravitational forces or gravity has got no influence on the motion of gas molecules.
Okay, so anybody who knows anything about entropy and thermodynamics knows that this can't be done justice in, a 15-minute little discussion. These are the points that I'm going to tackle. So I'm going to start with what is pressure. So, pressure is defined as the force per unit area. So in other words, I have to have a force upon an area. And with gas pressure, this is my living room and these are the particles flying around. Gas pressure occurs when the particles bounce off the walls or bounce off the ceiling and they create a force.
Please clap.
Now the force, we can even calculate, it's the rate of change of momentum of each particle. Just throwing that in there for no reason really. But when they bounce off the walls, they create a force, and the force upon the area of that room will give us the pressure. We know at sea level the pressure we get is about 14.7 psi.
He could be determined to be right, because without something for the particles to be striking, you're not going to get that change of momentum. But that doesn't mean that there has to be a dome. All that means is I just take the balloon away. Without the balloon, these air particles aren't going to be striking anything. Therefore, there is no pressure. Without the balloon, these air particles aren't going to be striking anything. Therefore, there is no pressure.
But if I take a gas, that gas is going to spread out and increase its volume at any given temperature, and as I increase the temperature, the gas is going to spread out even more. And if I increase the amount of gas, the amount of particles there, it will spread out even more.
Okay.
Now we know this, and anyone who studies sort of like molar calculations and with gases, we know that 1 mole of a gas at a given temperature will occupy a certain volume, and if I increase the amount of gas, it's going to occupy a bigger volume. What if I stop this gas being able to spread out? What if I put it into a container? So here is the gas. Now this time, as I add more gas, it's not going to make this. It's not going to make the gas increase in its volume. I have fixed the volume. The volume now cannot change.
That's correct.
So as I add more gas, what happens is there are more collisions between these gas particles and any surface that's inside. Now that will include the inside of the container, but also anything like a balloon that I might put inside the container. So the pressure per square inch is going to increase as I add more and more and more gas, because I've got more frequent collisions.
Please clap.
Now this is really what we mean by pressurized. If I take the walls away, then that gas will expand, and it will expand to a given volume dependent on the temperature and the number of moles or the number of particles of gas that I've got. So basically the Earth does not behave as a container with a fixed volume of gas. So basically the Earth does not behave as a container with a fixed volume of gas.
velho. Pelo amor de Deus, cara.
So basically, the Earth does not behave as a container with a fixed volume of gas. So basically, the Earth does not behave as a container with a fixed volume of gas, and that would mean that the pressure is directly proportional to the temperature. So as the temperature would double, the pressure would double, but we don't see that relationship. We don't see huge changes in pressure at sea level as the temperature changes. We don't see huge changes in pressure at sea level as the temperature changes. Now, for those a little bit more advanced, we'd have to convert the temperature to Kelvin and not degrees. Essentially, so gas pressure on Earth just does not behave like pressure in a container behaves. It just doesn't. We do not have this fixed volume capped by a dome. If we did, we would have a fixed volume of gas, and what we would find, like I've said, is if I increase the pressure, I would get I would get a proportional increase in pressure. We don't see huge changes in pressure at sea level as the temperature changes. You show me a container anywhere on Earth, where I can increase the temperature and the gas inside will have varied responses to the response in terms of its pressure.
Okay.
You won't be able to find one at all because it doesn't exist. Is if I increase the pressure, I would get temperature. I would get a proportional increase in pressure.
Hello, everybody out there in YouTube land. Good times for all, or Zachary Zabala here if you prefer. In this video, we're going to explain what we're doing here, and this is just a very rough start, folks. What we have is a bucket of ice water. Okay? This is a little too warm to be touching right now. This is one of these turned over. It has one of these in the bottom of it upside down in the ice. It is held up. Oh, it's held open right now. So, and that hose is coming out right here, and it runs up to this pressure reading gauge right here, which, as you can see, is right at about 3. And this one is right at about, it's under 2.5, almost to 2. What I've done is I've taken this heating gun up to 800 degrees, and then we have the bucket of ice water at the bottom, and I'm changing the temperature, hopefully, at both ends. So we have the cold at the bottom and the heat at the top. And what we're finding is that we're getting a little bit more pressure on the bottom. Just a hair, possibly. What we really need is another one of these gauges right here. Now, in fact, these gauges may not be 100% accurate. They're old. Some of them are sticky. So this is really just a rough start, folks. This may not actually be doing what it looks like it appears to be doing. So that one's at about 2. We need this one. It appears it's at about 3. So we have, we need better equipment. But I think we can get pressure change from one gradient to another inside a sealed container. There's definitely a huge heat swing that we have here on Earth. As you go up, it gets much colder, and then it starts getting warmer again. they say much, much warmer. The highest I've seen, it still only gets like to 7 degrees, but it was negative 65 at one point, and then it starts warming up. So I started, instead of doing the heat on the bottom and the cold on the top, I did the heat on the top and the cold on the bottom. And this is trial number 1 you're seeing right here. So I'm really just throwing this out here so other people can maybe try it or give me some ideas to make it better, really.
But of course these guys will just completely ignore that. So let's move on to number 3. What is entropy? Good question. Now I could be here a long time with this question, and I'm not going to be. Like I said, if I get sensible questions and request space on this, I will do more. But essentially all we need to know at this level at the minute is that it's to do with the spreading out, but it's not to do with spreading out of mass. And this is what, again, flat earthers would have you believe. If I have lots of gas particles here, we do know they are going to spread out. But it's not the spreading out of the gas particles that follows entropy. What entropy is the spreading out of energy. If I take these gas particles with the spreading out, and I was to measure not to do with spreading potential energies, to do with the then I have a lot of energy, but it's not to do with space. When they spread out, they are dissipating that energy spreading out. But it's not to do with spreading out of mass, and it's to do with the spreading out. But it's not to do with spreading out of mass. And
Hi, I'm Emerald Robinson, and in this What Is video, we're going to investigate the state of matter called a gas. Gases are materials that have no definite volume and no specific shape. In other words, gases can easily flow into and take the shape of a container and will expand, redistributing themselves to evenly fill that container. Although there are many types of gases, there are a few characteristics that they have in common. First, particles in a gas have no real arrangement. They can move over and past one another, and the space between the molecules can increase or decrease. Molecules in a gas collide with one another and move more quickly or more slowly based on factors like temperature and pressure, but they will always spread out fairly equally to fill the space that they're in. All of this molecular movement means that gases hold a lot of kinetic energy, energy caused by motion. Second, gases can be compressed. Because there is space between the molecules in a gas, it can be placed under pressure and squeezed so that the particles are forced to be close to one another. Third, gases can flow from one area to another, although the direction of flow is not directly affected by gravity. This ability to flow means they are sometimes referred to as fluids.
So that was the opening video. Hey everybody that's just joined, good to see you. We just watched it's about almost 15 minutes long. I hope you guys paid attention. You guys in Ellemnet, did you guys pay attention? Or try?
Yep.
That's actually quite straightforward, correct? What do you think the main points was shown there?
Gas behavior.
And what?
It was definitely the spreading out of things, as he said. His cards put it.
Pressure requires a container.
Yeah.
Like gases, if it didn't have a container, would fill the available space of the next place. You know what I mean?
Yeah. And what did it say about gravity?
Yeah.
Didn't tell you about gravity.
Ooh.
It said it has
You don't think about gravity.
It said it has no effect on the direction of gas flow. No effect at all. Someone's got a lot of background noise. It's Michael.
It's my mother.
Hi, Mrs.
Tell my
Michael.
mum to shut up.
Hi,
Talking
Mrs.
to a
Michael.
different cat.
So yeah, it's very simple. Most of it was there. I just had to add Cats with his showing he doesn't understand entropy. Okay, so what do we take? First of all, gas has what we call elastic collisions. Do you guys understand what elastic collisions are?
Sort of.
Yeah, elastic collisions is simply there's no transference of energy when they collide. So they can only change direction if they hit another surface like a gas particle or a walls of a container. Yeah. So they can only change direction with a collision. They can't change direction in any other way. So since gas is always moving in straight lines constantly in all directions with great amounts of kinetic energy, they cannot fall back down to Earth as the globers love to push. It's just total poppycock. It's not demonstratable. It goes against the molecular law or theory of gas molecules, and it goes against gas behaviors. Now we know gas behavior is always noticeable. It's a natural law. So
You know, if you blew a balloon up, it'd always look like a pancake, wouldn't it? If gravity were pulling gas molecules down.
yeah, it wouldn't be moving in all directions. It would just simply go pool at the bottom, and why would you need a balloon then? We could just walk around with buckets of sulfur hexafluoride. We don't need to put them in closed containers. And this is the problem that Phil had when he did his 2-hour very boring presentation. At the end, all he was doing was look at the black stuff. that means it's not violating second law of thermodynamics. Full. But yeah, what can we say? It's very, very simple. All gas laws prove that you need containment, and the fact that gas has elastic collisions shows that you will not have space being able to exist, because the gas you breathe will evacuate into the available space. So then we would die because everything would just be gone. Oh, PJ. So yeah. You guys want me to start my presentation maybe?
What? Are you asking us?
Yeah.
Do we want you to start your presentation? Well, that's what we've come here for, isn't it?
I hope Phil's paying attention. So, okay, guys, this is very...
Phil's digging them credentials out. That's what I hope.
Yeah, probably.
Well, you saw how much numpty clips I'm putting off Phil, comments I'm putting off Phil in Ellemnet these days. The guy's proving not to be a professor, that's for sure.
That is.
Yeah.
I refuse to call him a professor until I see evidence.
Yeah. I mean, the guy's saying scurvy is not the cause of vitamin C deficiency, for Pete's sake.
Yeah.
Okay. So like I said, guys, this is just like I will probably do later on a more in-depth one, a bit more at a different level. So this is more so everybody can understand in very simple terms what's going on. Okay, so thermodynamics, why it destroys the space vacuum. Ooh, I think it's very catchy. What is thermodynamics? Thermodynamics is simply stated as the science of energy. It's a natural law. I just have to state it's a natural law because they call it... Ooh, PJ. You might need to mute, mate. PJ? You muted. Okay, anyway, they call it science of energy, so I'm just going to say no, it's actually just, it's a natural law. When they say it's the science of energy, it just means it's the principle of energy, in other words. So, the word thermodynamics stems from the Greek. Therma meaning heat, dynamics meaning power, so heat, power. It's the principle that deals with the heat and work. So this is the principle that runs your car engine, combustion, your refrigerator, your geyser, your heater boiler, and so on, so on. There's so much things. Even your kettle works off of this principle. What is thermodynamics? The understanding of thermodynamics is used in everyday living. Mostly everything you use today is based on thermodynamic understanding that you have usable and non-usable energy. Let's start with a combustion engine. On screen here we got a little cylinder wall inside with the combustion. It's got a piston, it's got a conrod and a crankshaft, and then obviously it's got the inlet and outlet ports with the valve springs and the injectors and the spark plugs. Well, anyway, when it is closed totally, you see it's a closed system, it lets heat in to the closed system, it has a boundary, and then as soon as it expands, it pushes out and it does work with that heat. So how this works is simple. Energy is from heat transformed into work. As the gas expands, that would be combustion, it works as a result, it cools down. So as it's working, it's using that energy and it's transferring it to another for work. So in other words, it cools down. That's why you have, when you have a hot cup of coffee and you just let it sit, it's cooling down. That heat energy is dissipating into the surrounding system, and it's causing the gas molecules around the cup in the system to move around faster. In other words, it's moving, it's working, and therefore the coffee is getting cooler. The energy was transferred to move the piston that is attached to the conrod, and which attached to the crankshaft, and which turns the flywheel. So the combustion inside this closed system, guys, remember when it's closed, it combusts, it explodes, and that combustion inside that explosion pushes the piston down, which in turn forces the conrod to turn the crankshaft, which is connected to the flywheel, and that's what makes your car move forward. This is usable energy. It's using the energy required from the combustion in the engine. Now we have to know about thermodynamic systems. A thermodynamic system is very important to the understanding of this principle, as it denotes the transfer relationship between a system and its surroundings. So in just simple terms, you have an open system. We just have gas molecules inside the system. We can see matter and energy can pass through its boundaries. So in other words, if it's open, it can pass through and out. So if a gas can leave the system, it can come back. If you have heat leaving the system, the heat can come back into the system. This would be sort of like a cup of coffee, as we said earlier, or a cup of tea. It's an open system, and so for the energy can leave. If you pour the cup upside down, all the coffee or tea inside the cup can leave the cup. So the matter and the energy can leave. With a closed system, the matter cannot leave, but the energy can leave. This would be, let's say, like an ordinary closed container. Let's say you have a container and you stick it in front of a heat source. It can be heated up because the energy can come from the surrounding system into the system of the container, and it heats up everything inside there. So the energy can be transferred from system to system where the matter cannot. So you can shake that around, everything turn upside down. Whatever's inside that closed system cannot go out to the surrounding system. So let's say it's a bottle of water that's closed. You can heat that water up and the water can cool down, but you can't throw the water out or put water in if it's closed. An isolated system is just a hypothetical system. This would be for the boundary, as they would usually equate this to the universe. You have no matter or energy being able to go through the boundary, because that is the end all of everything. There's no system beyond the isolated system. Now you do get times when they try and explain it in simple terms with like a thermal flask. We're saying you see it doesn't let any heat energy in or out, or any matter in or out, but that is false, as it's just a hypothetical. It will still have energy leaving the system and it will still get cold. It just takes much longer. Okay, now we move on to some gas laws. Excuse me, just give me 2 seconds, guys, just talk amongst yourself.
that happened? I don't know what else to say.
Okay, sorry about that. The children should have been sleeping quite a while ago. Anyway, all gas laws abide by thermodynamic law. The reason we're going to go through gas law is because it's pertinent to the argument, especially when it comes to we have to understand that gas has behavior. So no more greed, gas definitely has behavior. And how it works with our observations of everyday life. So the behavior of gas will always abide by thermodynamic law. What gas laws are there? Well, we'll start off with Boyle's law. It states that the volume of a given amount of gas held at a constant temperature varies inversely with applied pressure when the temperature and mass are constant. So if you have a container and you're keeping and you're varying the temperature, but you're keeping you're holding the constant temperature, and you keeping the volume, it changes. So if you have more heat, it's going to create more pressure. If you have less heat, it's going to create less pressure. So if you push down and decrease the volume, it increases the pressure, and if you increase the volume, it decreases the pressure. It's simply that, because gas moves in all directions constantly. This is why we try and explain, if you go higher up in the atmos plane, I'm not going to say sphere anymore, atmos plane, there's a wider area for the gas to move around. So there's less pressure because the gas has more place to bounce around. You understand? So the more the gas can move around, the less pressure, keeping with Boyle's law. Then we have another one, Avogadro's law, one of my favorite gas laws. Gives the relationship between the volume and the amount of gas moles when the pressure and temperature are held constant. So if the pressure is held constant and the temperature is held constant, with the amount of gas, it would give you your proportionate. So with a volume 1 and the amount of let's say the volume of the one system is over to the number of moles of the one system is equal to the volume of the second system with the number of moles of the second system. So that's how they work. And then we get to Gay-Lussac's law, states that the pressure of a given amount of gas held at a constant volume is directly proportional to the Kelvin temperature. So this is just to give in Kelvin temperature. If you hear, usually like we would talk usually with kelvins, and I say to like Professor Forbell, show me where in reality you get something at 0 Kelvin. That would be minus 273 degrees centigrade. You can't get it. It's impossible because it's the absolute temperature. You can't get absolute in nature, so therefore gas can never stop moving, and therefore gas cannot fall down to earth, as they love to call it. So this just simply tells you the relationship between the Kelvin temperatures and the gas held at constant with the volume. So if you're going to keep the volume the same, and you're going to directly change the temperature, it's going to increase the amount of molecules, because the gas is getting kinetic energy and they're bouncing. And remember, they do not transfer any kinetic energies because they have elastic collisions. They will just have more pressure, so you're just having more collisions more frequently. Now, what do they all have in common? What do you guys say all these gas laws had in common? Panel?
That they're laws.
Yeah, and? They all had containment, correct?
Yes.
And they were all intermingled in some way. They were inversely. Let's put this so that the pressure, the temperature, and the volume were all linked.
They're all correlated to
Exactly. And the gas is always moving in all directions in straight lines. And elastic collisions. Yeah. Kind of goes weird. It goes against what the globe claims. Gas go down, go boom boom, as they love to say. Has any of those gas laws stated that gravity does anything to the direction of those gases? Or uses up their energy?
Not, well, it can, but that would be an outside influence.
Yeah, because you have a force on the outside. But gravity is not a force anyway, so it wouldn't be able to do anything. And even if we gave gravity as a force, it would not even be able to do anything because it's far too weak. And that's giving it to them, which is impossible. But yeah. Okay, so containment was required. Whoopsie. So the fact we have gas pressure and we have the gas laws that we can experiment and demonstrate continuously shows us that we have to have containment. You cannot demonstrate any gas law without having containment. You cannot observe any gas pressure without having containment, because that's how it works. It's an antecedent. It goes against the mere nature of what a gas pressure is if you have no containment. So now we move on to the quick raw of kinetic molecule theory. This tells us that in a given collective volume, of all particles having free space between them to move around freely, we can determine the behavior of the particles. So all the gases are moving around freely all over the place, and we can use this to determine how their behaviors are set and that they have free space in between them. This is what Dell seems to not understand, because he says, if you have a gas particle here and here, what is between them? How do they move together? That's the whole point. The gas move through free space together. Okay, so postulation 1. Gases are composed of a large number of particles that behave like hard spherical objects in a state of constant random motion. I want you guys to concentrate on keywords here. Constant random motion. That would be the Brownian movement that the one guy was talking about in the video. It's just moving around in all directions constantly. So they never stop moving. They just move up, down, left, right, center. They have a collision. They change direction, have a collision, change. That's how gas behaves. Now this is constantly, it never stops. They never go static. So these particles move in a straight line until they collide with another particle or the walls of the container. Does it say anywhere they stop moving because of gravity? No.
Nope.
Exactly.
Gravity is a myth.
Exactly. So these particles are much smaller than the distance between the particles. Most of the volume of a gas is therefore empty space, and this is them trying to explain why gases are compressible, because there's empty space between the molecules. So when you compress it, then you can get outcomes. You can get the phase change and liquid, obviously, because that's why gases are compressible, because the empty space between them. So number 4, there is no force of attraction between gas particles. Get that, guys? So no gravity between gas particles. They don't, attract each other. Mass attracts mass kind of thing. Or between the particles and the walls of the container. So there's no attraction whatsoever. They are just simply in their own world, bouncing all over the place, changing directions when they collide with another particle or container wall, surface, or whatever. They're just bouncing. That's the only way they can change direction. Postulation 5. Collisions between gas particles or collisions with the walls of the container are perfectly elastic. Globers, I want you to pay attention here. What does perfectly elastic mean? That means there's no transference of kinetic energy. So when the two particles collide with one another, they do not impart and transfer any kinetic energy. They just simply bounce off back to another vector. They bounce off and bounce away from the gas particle or the container that they've hit. So in other words, they keep their kinetic energy. None of the energy of a gas particle is lost when it collides with another particle or the walls of the container. Okay? So if a gas particle, let's say, hits the ground and it bounces up into the sky, it will never return unless it hits another surface, another particle, or the walls of the container to bounce back. The mere fact we have gas to breathe shows the antecedent that there is a container for the gas to bounce back to breathe. The average kinetic energy of a collection of gas particles depend on the temperature of the gas and nothing else. You see, this has got to do with the thermal energy. So the kinetic energy of the gas itself, you know, when we say the jiggling of the atoms inside, the molecules, the particles and molecules, they're moving up, you know, jiggling faster and faster. That's the kinetic energy which causes it to move faster. Now note again, when we say gas can never reach absolute zero. They cannot reach 0 Kelvin, so they would never be able to be static. They will always move constantly until they have a collision. Now, when something goes further away from the warm surface of Earth, they are obviously cooling down because it's work being used, but it does not transfer kinetic energy onto another collision of another particle. So it just moves until it finally hits something to bounce back. So then we can move on to Monton's law, which is the last postulate of the kinetic molecular theory, states that the average kinetic energy of the gas particle depends only on the temperature of the gas. Thus, the average kinetic energy of the gas particles increase as the gas becomes warmer. Because the mass of these particles is constant, their kinetic energy can only increase if the average velocity of the particles increases. So if it's moving faster, that means it's increased with kinetic energy because it's got warmer. The faster these particles are moving when they hit the wall, the greater the force they exert on the wall. Get it? So if a particle is zooming 5,000 miles per hour and hitting the surface wall, it's more force than when it's moving 3,000 miles an hour hitting the surface wall, in other words, just as an example. Since the force per collision becomes larger as the temperature increases, the pressure of the gas must increase as well. This was exactly saying more collisions per time, and the faster it's going, so it's hitting the wall at a stronger force. And note again, it has perfect elastic collisions, so never transfers that energy to the wall or anything else. It keeps it. So Dalton's law of partial pressures. The globies don't like Dalton's law of partial pressures because this is the conglomerate of all the gases in our atmos plane. Imagine that it would happen if we had 6 ball bearings of a different size were added to the molecular dynamics simulator. The total pressure would increase because there would be more collisions with the walls of the container. This would be as if you take a room and you stand in front of a wall. No, let's say you lie on your back and you got a roof, and the roof is free falling. Okay, it's loose. And we're all lying on our back, and some of us are throwing some tennis balls to try and keep that roof up. Now, you would agree that if we got 50 people lying on the back, it's going to be easier to throw the balls and hit that roof to keep it up than it is with 10 people. Because there's more collisions more constantly, so it keeps it up. But the pressure due to the collisions between the original ball bearings and the walls of the container would remain the same. So the pressure remains the same because the collisions and the walls stay the same, because remember, it's elastic. So there is no more empty space in the container that each type of ball bearing hits the walls of the container as often in the mixture as it did when there was only one kind of ball bearing on the glass plate. Remember, there is a mixture of gases. Every gas has different densities, they have different molecular weights, and they move at different velocities. So something's going to move faster than another one, other one's going to move slower than that, and therefore it's going to be a constant pressure push on that wall. It's like taking turns to hold up the wall, you can say, but the impulse is just so sudden it just hits and bounces off, but obviously the one will move faster than the other. So the total number of collisions with the wall of this mixture is therefore equal to the sum of the collisions that would occur when each size of the ball bearing is present by itself. In other words, the total pressure of a mixture of gases is equal to the sum of the partial pressures of the individual gases. Now we can move on to, you guys can stop me anytime you want, by the way, if you want to ask questions. So, Graham's law of diffusion and effusion. This is something that Professor Phil Bell also didn't understand. A few of physical properties of gases depend on the identifier of the gas. One of these physical properties can be seen when the movement of gases is studied. In 1829, Thomas Graham used an apparatus similar to the one shown in the figure below. Okay, I'll show you the figure soon. To study the diffusion of gases, the rate at which two gases mix. So this apparatus consists of a glass tube sealed at one end with a plaster that has holes large enough to allow a gas to enter or leave the tube. This is sort of like, let's imagine a tire that's got a hole in it, okay? When the tube is filled with H2 gas, the level of the water in the tube slowly rises because of the H2 molecules inside the tube escape through the holes in the plaster more rapidly. So what happens? Remember when we say you've got a small hole, it's going to seek the available volume. So as it's moving, it's creating a low pressure system, and therefore it's going to keep the water to rise. The molecules inside the tube escape through the holes in the plaster more rapidly than the molecules in the air that can enter the tube. So in other words, it's forcing out at a greater rate than what the air can come into the tube. That's why it has creating the pressure system differential. By studying the rate at which the water level in the apparatus changed, Graham was able to obtain data on the rate which different gases mixed with air. So it gives the rate of diffusion as equal to what? The gas over the density. So the density determines the movement, not gravity, guys, not the mass, it's density. So Graham's law is easy. This is what I was talking about. The diffusion is equal to the particle movement from the area of high to low concentration. So it's high concentration, it's moving to low concentration, it's spreading out. If we have it like this with the effusion, you see the diffusion of gas particles through an opening. It's got an opening, so the gas is bouncing all over the place and it's forcing itself through to the available spot. What would this entail for the Earth? If Earth was an open system, it would simply just move to the available volume. It would force itself through to the available volume, and we would not be able to breathe because we would all be 10 to the minus 17 torr at the moment. So what is an elastic collision? We kind of alluded on this earlier. An elastic collision is a collision in which there is no net loss in kinetic energy in the system as a result of a collision. Both momentum and kinetic energy are conserved. The quantities in elastic collision. So the momentum and the kinetic energy stays exactly the same. They stay conserved. They will never ever change because it does not transfer or lose energy with a collision. Suppose two similar trolleys are traveling towards each other with equal speed. They collide, bouncing off each other with no loss in speed. This collision is perfectly elastic because no energy has been lost. Obviously, it's not going to happen with a trolley, but it's just an excuse to make you visualize it. So imagine two trolleys coming towards each other at, let's say, 50 miles an hour each, and they bounce away from each other at 50 miles an hour each again. That's how it works. In reality, examples of perfect elastic collisions are not part of our everyday experience. Some collisions between atoms in gases are examples of perfect elastic collisions. However, there are some examples of collisions in mechanics where the energy lost can be negligible. These collisions can be considered elastic, even though they are not perfectly elastic, just like the billiard balls. Collisions of rigid billiard balls or the balls in a Newtonian cradle are two such examples. These are the billiard balls. You see, they're imparting they're almost negligible that they can be considered as a elastic collision. But eventually, because they are not perfect elastic collisions, they will, with a long period of time, end up becoming less and less and stop. Okay, and that's what I got to so far with my presentation. Hope that made sense to you guys. I see I got a super chat. Was it nice and simple? Hope it was simple enough.
Yeah. Well, I think some people probably may have gotten lost, but to me it was simple.
Well, I'm happy it made it simple to you. But like I said, I'll do a more in-depth next level one with some, that makes it more, how can I put it, with I'm trying to think of the word. I can't think of the word. But anyway, we'll make the next one a bit more complicated so people can understand it, that think this is too easy for them. Anyway, Jonah Edwards, thank you very much for your $10 super chat, mate. Really, really appreciate it, mate. You rock. Thank you very much for your super chat. So any questions?
No. Unless there's some in the chat.
It's good to see everybody here. Thank you for coming. Thank you, Ian. See, it wasn't 2 hours long and it wasn't as boring as Professor Phil Bell. And I just wanted to bring up points that show Professor Phil Bell his argument just wrong. I see Michael and PJ left. I know PJ is struggling with signal and Michael struggling with his phone, so yeah. But that wasn't 2 hours long. No, I definitely won't have a 2 hour presentation, Rachie. It was unnecessary from him. Anyway, Brainstein says more in-depth isn't going to help those people who didn't manage to follow this one, is it? You need less in-depth. It's true. But I'm saying the more in-depth one will probably be for advanced, for the people that want to learn in advanced ways. But this was very simple down way to make even people like Professor Phil Bell understand. You see that black stuff? It's in the same system.
Yeah.
He doesn't get that.
No.
Wow. So anybody in chat, if you guys have any questions, you want to just come and talk about it, please feel free to come in. It's just good to have you guys here. So that was thermodynamics in a nutshell, how it destroys the globe.
Mm-hmm. And it does.
Mm-hmm. I guess that was it.
No, it was a good presentation. It was very well explained.
Thank you. Like I said, I wanted to do a better one as well, but I just didn't really have time. I was literally creating this presentation every 2 minutes as I get a chance. Like little pieces here when I'm on lunch or when I'm spraying a car and I just have to wait for flush off, I'll quickly carry on. But that's practically all I could do. Just when a person's very busy, you suffer.
Yeah.
But let's see, we got 54 votes already for law of entropy. First law, 13%. No.
Wow.
The first law is the conservation of energy, guys. And the second law is the law of entropy. Third law is definitely not the law of entropy. And the fourth law is just the zeroth law, guys. But it's good to have you guys here. Blue Pool, hey, haven't seen you in a while. Thank you for coming. We can go look on some videos of demonstrations of the different gas laws if you want to.
You want to look at the demonstrations of other gas laws?
Of just gas laws, yeah. We can do that because, I mean, I think to visualize it makes it easier for people.
Yeah, I believe so.
I've shown this one a few times before. Whoop.
Sorry, guys, I had to go back onto the old computer. For some reason, the new computer is just jittering. It's going slow, and the sound is just like it keeps cutting out. So I don't know what's wrong with it. I haven't got a clue. Might have to take it back.
Okay. But that's your new computer.
Yeah, that's the new one. Yeah.
Oh.
Yeah. But it's not just the sound. It's slow. Everything's slowed down. Like when I was trying to mute, it wouldn't let me mute. I had to click it about 100 times before it mute. And when you were saying something like you're gonna have to go and mute, there was no noise coming from my side at all. So the computer must have been doing something. I haven't got a clue. But yeah, there you go. I think we're going to take it. But I'm so gutted because I like it so much.
But it's good to have you, Blue Paul. Okay, so what do you think is happening here, guys? This is Boyle's Law. based on the presentation, I explained this. So as the pressure around the system is decreasing, it's becoming available, and the gas inside the balloon is seeking to fill the space. So it's creating a larger volume. So the balloon inside is expanding, all the gas inside is expanding to fill the available volume. So the balloon itself is expanding into the lesser volume, and therefore it's equalizing. You see, it's trying to equalize.
The balloon expands to try and equalize the pressure. Volume and pressure are inversely related to each other.
So volume and pressure are inversely related to each other, guys. So we we take the pressure away. If the volume expands, the pressure decreases. They're inversely proportional. So when you have the same amount of molecules inside the system and you're just expanding the volume, they have to travel further. Okay? So therefore the pressure becomes less. Now, with the outside system being a vacuum, there's no pushback on the gas inside the balloon, and therefore the balloon can expand outwards to fill the available space. They're going to give more examples soon. Now guys, this is based on Boyle's law.
Another demonstration of Boyle's law, we will put a marshmallow peep into our vacuum jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the peep will expand to try and equalize the pressure.
So that's practically just what Boyle's law is about, guys. I think this is very telling what would happen with our gas if Earth was an open system. Everything on Earth would just degas. It would literally just try and fill the available volume. We would all just boil alive here. We'll die. Jeff Conkle. Globies will call gravity on the shape of the balloon in that demonstration. Notice that the balloon wasn't round when it expanded, Jeff?
Yeah.
Yeah. Because they don't understand, it's not gravity that makes it round. It's the air pressure around it. Gas is hitting it from all directions constantly. Sit on here. Sit on here. Sy wil nie sit nie. Sit on here. So moving around constantly. So that's what gives it that spherical shape, because it's all around the balloon. Okay, let's see. What's the next one? You want to go to Avogadro's law? This is a nice one. This chemistry demonstration lab staff have been professionally trained to use the chemicals and equipment shown. Please do not attempt these demonstrations on your own. How dare you tell us not to demonstrate on our own? It's simple. Just don't drink the stuff.
Delicious.
Yeah. No, oxygen is invisible. You can't see oxygen. But you definitely know if there's no oxygen, you would not be able to breathe. Okay, you know what I'm going to do? It just works better if I do it. If I do it in my other browser for some reason. I don't know why. But if I try and use my YouTube on Chrome, it just wants to buff. But at least I have ad blocker on there, but I don't have ad blocker on this browser.
That's probably why it buffers. It's the ad block.
Probably. No, but I did it before I had ad blocker though. And it's only on Chrome. Really weird stuff. Okay. Ooh, beautiful.
Let's take a look at limiting reactants. Each of these flasks has 190 milliliters of 1 molar acetic acid.
Mm-hmm.
How many moles of acetic acid is that?
Well, anyway, guys, so they're giving a constant molar count, okay? So it's all got exactly the same amount. Remember what it said? If you've got the same amount of gas and then you change the temperature or the volume, and then it gives inversal proportion behaviors again. But the amount stays the same. You just either change the volume or you change the pressure, and therefore it will change. So if you change the temperature, you know what happens, the gas expands, but it's still the same amount of gas, and therefore you will have a different reactant.
These balloons have differing amounts of sodium bicarbonate: 4 grams, 8 grams, 16 grams, and 32 grams. How many moles of sodium bicarbonate are in each of these balloons? Can you determine the limiting reactant for each flask?
Just go to where they actually plop it in. We don't need to see. Okay, so look what happens when they throw it in.
Next,
Ooh.
8 grams.
Where's your gravity now? I don't see gravity happening. You see, more amount. The amount is larger. What's happening? Same amount, but it's the same volume, correct? The container's the same amount of volume. Ooh, look at the reaction. See, it's getting bigger and bigger, guys.
As expected.
Exactly. So that's just simply Avogadro's law, keeping the amount constant, and then you're changing the parameters around the amount of moles. So you can change the volume, you can change the pressure, the temperature, and that is what will give your reactant. Okay, then we have Avogadro's law now. Let's use Gay-Lussac's law. I can never get over the name. Okay, demonstration.
Alright, so as we've explained...
And Jonah Edwards. If she was hot, the balloons would pop. What?
With Gay-Lussac's law, his law states that pressure and temperature of a gas have a direct relationship.
Mm-hmm.
Meaning when temperature is increased, pressure will also increase, as long as volume and the number of moles of gas stays the same.
Okay, so they keep the number of moles in the gas exactly the same. Okay, so the volume stays, the container's the same, and the number of volume stays the same. They're just increasing the temperature and the pressure because they're inversely proportional to each other.
So what we've done is we have increased the temperature of the gas inside of this can to boiling temperature. And I'm going to put it into this beaker of ice water, thereby decreasing the temperature of the gas in the can. Let's watch what happens to the pressure.
Ooh. Ooh. Okay, let's put this into terms of Earth and space. What do you think happened there? Let's say this was the tin can, was the ISS, guys.
Well, it compressed.
What happens to the ISS supposedly in space? Getting heated and cooled constantly, correct? Every 90 seconds it sees the sun and doesn't see the sun, correct? And those
apparently.
Yeah, and those temperature variations are on magnitude of quite a large magnitude. And aluminium is very susceptible to heat conducting. Conducts heat really well. So if it gets into the sun, it's going to heat up very quick. If it gets out of the sun, it's going to cool down quite well. So, really weird. Let's put it this way. Have you guys ever held one of those aluminium CD cases before, and it feels cold when you touch it?
Yeah.
That's because it's a good conductor. It conducts the heat out of your hand, so it feels cold. But let's say you take a Bible or a book or something and you hold it. It feels warmer than the aluminium block that you were holding, correct?
Yeah.
But what if I told you they're exactly the same temperature? The one just feels colder because it conducts the heat easier. Yeah. So that's what we're saying. If the ISS is so-called aluminium, and this is begging the question that they can violate the second law of thermodynamics, just this alone would crush the ISS.
NASA just violates all sorts of laws.
They violate a lot of laws. Because that's Gay-Lussac's law. Which one haven't we done? Boyle's law, Gay-Lussac's. Dalton's law. Dalton's law of partial pressures. Hey, Nick Nimmin. Shout out to Nick Nimmin. He rocks. I use all his music, by the way, guys. He's got Creator Mix. His link is in my description if you guys ever want to use some of his music. It's for free. It's copyright free, so you don't have to have any worry about getting copyrighted for the music. Him and his brother make it for people to use. The only thing is you cannot use it to make your own music or music videos. That's all. But as long as you just put their link in your description, they're more than happy. But they're really awesome people. Okay.
Demonstration on Dalton's law of partial pressure, which states that the total pressure is the sum of all the parts. We're going to do this demonstration with two different chemical reactions that create...
This makes me think of the days when you're in school and you had to create a volcano.
Oh, yeah.
Yeah.
I remember doing this with the volcano, with the vinegar and the bicarbonate of soda.
Yeah.
Two different gases. We're going to do hydrogen peroxide and bleach in these two bottles, making oxygen.
How to make a bomb. Just joking. Yeah. When we were in school, we played around with bleach and milk in glass bottles. Not a very good thing to do, guys. One of my friends almost lost his eye. He ended up holding his eye in his hand while we rushed him to the hospital. Because we put it down and it was waiting for explosion. Like, why does it take so long? And he went to go check up on it, and it exploded as he got there. And well, the glass shot up into his face. Just blood everywhere. Wasn't a very pretty sight. I think he got 7 stitches by his eye socket.
Oxygen gas. And we're going to mix baking soda and vinegar in these two bottles, making CO2. We're going to start over here.
I'm going to like his video.
Mixing bleach.
Thank you, Tony.
In these two bottles with a balloon on top, which...
Yeah, Blue Pill. What? It's quite reactant.
Equal parts of reactants. These two balloons should be about the same volume. And then we're going to go ahead and do with this balloon baking soda and vinegar.
Okay, we're going to just forward and we're going to check.
Same size as these two other balloons.
Same size, yeah.
Together.
You see, this is how we were trying to explain to the globies when it comes to your atmosphere. Dalton's law is just the conglomerate of all the partial pressures together, which give you your 14.7 psi. It's as simple as that, and it's all gas. They still have to abide by gas law. They still have to abide by the laws of entropy. Just because you have an illusion of gravity doesn't make it real. Thank you, Jonah Edwards, for another $10 super chat, mate. Really, really appreciate it. Saying nothing again. So really appreciate all the support.
It's mad to know that he says nothing in his super chats because he talks quite a lot in chat.
Exactly.
He'd like to talk a little bit more. I say that in the best way, Jonah. I love you, man. You're cool.
Yeah, Jonah Edward is ace.
He is. He's brilliant, man. He's brilliant.
Go ahead and do this. We're gonna 12 mils of bleach.
Bleach, okay. Bleach stinks.
Bleach the bottles.
Yep.
And 20 mils.
Yeah, 20 mils. I'm going to say just stick his thing in here if you guys want to just go support him and say, hey, we checked your video out. Really liked it. Thank you very much. Because I mean, shame, the guy's only got like 42 subscribers. He's got 17k views. Very good. But yeah, do just go and hit him a like and say thank you for your demonstration.
About 20 mils of hydrogen peroxide.
And you know how hot that gets. It burns.
There we go.
There we go, check that. 1, 2.
This balloon.
My cat loves the smell of bleach. Really? I wonder why. Well, it does have a weird odor to it.
Those balloons should hold about the same volume there.
Lely's a powder.
Huh?
Is kom uit Lely's a powder in zijn junk.
Then, hold on, switch it.
With the children in the background, I can attest to that as well. Okay. Stick it in, come on. Shake it, shake it, shake it.
Yeah. Prepare this little baggie of baking soda.
Baking soda.
Not mix immediately with the. Can you come help me?
Yes.
Can you start that balloon on the.
Okay, give it a little shake. There we go. And there, look at the size of that.
There we have it. Oxygen plus carbon dioxide and a mixture. Each of their partial pressures adds up to a total pressure, the sum of each part.
You see? So, the mixture of them make the total pressure. So, the Dalton's law states that all the partial pressures in our atmosphere plane, well, I'm going to say atmosphere because I don't like the word atmosphere, makes our 14.7 psi. So, all the mixtures of the gases is what gives us the pressure, okay, in a system. What do we see here is required to have this pressure reading? A volume, correct?
Yeah.
So containment.
And containment, yeah, absolutely.
It's amazing how everything we have to demonstrate requires containment.
Absolutely. You can't have pressure without it. You know, you can't have a lot of things without it.
Yeah, and we haven't seen one demonstration without containment, which is really odd.
You couldn't have pools of water, hence you couldn't have a globe.
Exactly. INFE, thank you very much for your $10 super chat. Really, really appreciate it, mate. It says, Flurfs rule, Glurfs rule. I 100% concur, mate. Exactly. Thank you very much for your super chat. Gina Farrell, yeah, the second law of thermodynamics has never been defied by gravity or air gradients in a lab or in nature. Fake is 100% fake. Exactly. They can't violate the second law of thermodynamics. If anyone goes, who was it that said, I think it was Sir Arthur Eddington, whoever finds themselves going against the second law of thermodynamics should be laughed at into the deepest humiliation. I think that they said. And Jonah Edwards saying nothing again with another $13 super chat. Thank you very, very much for the super chat, Jonah. Really, really appreciate it. You rock.
I think he's typing an invisible link. That's what it is.
He's sending me space time, guys.
Yes, subliminal messages.
Thank you, Jonah Edwards, for your super chat. Really appreciate all the support, mate. So yeah, that's really, really odd. Okay. Any questions, PJ or Jeff? Or anything you guys want to add that I missed?
No, I mean, I was taking about half an hour to get the other computer set back up again, but no, so far so good. So far so good.
Oh, I got it.
Did Michael make his escape again?
Yeah, he just disappeared. This is actually very good.
Listen, you're a great...
Yeah, listen. Ancient ritual. That sounds dodgy. Okay. Bozeman Science, guys. Definitely a channel to subscribe to if you want to learn about physics and stuff. Really, really explains it in a very good way. I love the way he explains things. Swemmen die geld vanaand. Amper 20 randelas vir $1. Ja, Furious. Yeah, the rand's bad at the moment, so it is helping tonight. It's almost 20 rand to the dollar at the moment.
Wow.
So yeah, I appreciate all the support, guys. You rock. Okay. We don't need to listen to the music, but elastic and elastic collisions.
It's Mr. Anderson, and this is AP Physics Essentials, video 94. It's on elastic and inelastic collisions.
Yay.
Let's say we take a ball that has 10 joules of potential energy, and then we simply drop it on a table.
Whoopsie. Don't tell Daltards that, mate. They'll tell you the table dropped. They'll say he didn't drop, the table went up to meet the ball.
Yeah, absolutely. You can't drop a ball. You can't. It's impossible to drop a ball.
It's weird how it has 10 joules of energy if it's static. Think about that.
Yeah.
Now, it probably is not going to do that, but if it did, it would be a completely elastic collision. We converted that potential energy into kinetic energy, and as it bounced off the table, it returned all that kinetic energy back into the ball, so it was able to make it back again. Completely elastic. Now let's say we take another ball that is made of different material, drop it. It also has 10 joules of energy, but it doesn't bounce at all. We would call that a completely inelastic collision. Now where did that energy go? Where did the...
That way. It went that way. This is where impulse also comes in, guys. Just to let you know.
Those 10 joules of energy go, they became internal energy in the table and the ball itself that collided. Now we know that most balls are going to be somewhere in the middle, somewhat elastic in their collisions. And so during any collision, which could be elastic or inelastic, we're going to maintain linear momentum. In other words, the momentum of the objects before the collision is going to equal the momentum of the objects after. In an elastic collision, not only do we maintain linear momentum, we also maintain kinetic energy. The speed before the collision equals the speed after the collision.
So a gas, in other words. Yeah. So if a gas is going to have a collision, it can keep all its conservation of kinetic energy. It does not transfer it. So therefore, sorry, Bell, when you come and say things like gas will eventually lose enough energy that gravity will overcome it and pull it down, is poppycock. There's no such thing. And that's even giving them gravity, by the way.
Yeah.
Again, it's rare that that's going to occur. In an inelastic collision, we are still maintain linear momentum, but we've lost some of that kinetic energy.
Yeah, because it's transferred. It's lost energy, guys. Work done.
Where did the energy go? It became energy, internal energy, into the objects themselves. And so let me show you a collision between some Matchbox cars. Okay, so we saw two collisions there. And so one of those is elastic and one of those is inelastic. Did you figure out which one? So we call that an elastic and this an inelastic. So in an elastic collision, we maintain all of that kinetic energy. In an inelastic collision, some of that energy goes into the internal energy of the objects itself. If you think about two real cars running into each other, there's a lot of damage done inside those cars, and that's internal energy. It used to be kinetic energy that is doing the damage inside the car.
Yeah. You see, guys, why I like this channel. He explains it really, really well.
Yeah, definitely.
So, guys, do really go and subscribe to him. It's really well worth it. Explains things in a very easy to understand way, and he's doing this for physics students because they need to know these things to pass. You can say it's actually very good revision work. And I actually wish. Sorry.
No, I was just reading the bottom, elastic and explosion. Yeah, that makes sense. Definitely. Sorry, Carly.
No, sorry, because I'm saying I wish the Globies would actually go and pay attention, because the people I usually see that don't really understand what the hell's going on is the globe side. And not to mention Globusters, but the globe side, definitely. Which is really odd, because they're supposed to be these physics boffins, correct?
Mm-hmm.
Yeah, but they have to keep their delusion alive, so obviously they have to make shit up. Play dumb or make stuff up.
Let's start by studying some elastic collisions, and we're using a SimBucket simulation where carts will collide with each other. You can see on the left side that we have a 1 kilogram cart is traveling at 5 meters per second. That means it's going to the right. And then we have a 1 kilogram cart that's traveling in 2 meters per second to the right.
Yeah, 2 kilograms. Okay. So yeah, you see they travel at a different initial velocity. Okay? One is 2 kilograms, one is 1 kilogram. Okay? The 1 kilogram is moving more than 2 times faster than the one that's 2 kilograms. That's double its mass.
The right. And they're going to bounce off of each other. And now we have some new velocity.
So what did that show, guys?
Elastic.
It transferred energy.
Yeah.
Velocities after that collision.
So
was linear momentum maintained? Well, it's always maintained in a collision, but let's study that. If we look at the conservation of linear momentum, P1 plus P2, in other words, the momentum of those two objects before has to equal the momentum after. So M1V1 plus M2V2. So if we were to say M1 is 1 kilogram cart going at 5 meters per second, and then a 2 kilogram cart going at 2 meters per second. So this is the momentum before.
And equals then the momentum after. There we go. Very simple stuff.
Does it equal the momentum after? Well, if I multiply that out, it's 9 kilogram meters per second on both sides. The positive value indicates that the overall momentum of the system is towards the right, but it's equal, and it always will be equal in every collision. But did we maintain kinetic energy? To do that, we're going to have to use a different formula. Kinetic energy.
I know someone who studied physics and studied further into a chemistry field. The main thing I remember about him, though, was him always talking about faked moon landings. Wow. Well, that's the thing. Actually, it's quite interesting. There's a lot of people that did study further physics, and they say it's impossible for the moon landings to have taken place if they study further. But then you get some people that take the same classes, and then they just believe it because they're such a NASA fanboy.
Yeah.
Brainstorm, oh come on Flats, you're doing this whole thing for your FE side, and it's still too complex for any of them to understand, isn't it? Nice one, Brainstorm. No. We explaining it to you Globies because you guys think that gas just stops moving and then would come back down. That's why we're doing this. The mere fact that we can show this proves, yes, I'm going to say the word proves, space as a vacuum is fake and we have containment. Very simple stuff.
In has to equal kinetic energy out. It's an unwieldy formula. And so again, it's just 1/2 mv squared. That's kinetic energy, remember. This would be of object 1 and 2 before and then after the collision. So if I plug in those values here, what we find is that the 16.5 joules we had before the collision equals the 16.5 joules that we had after the collision.
Yep.
This is an elastic collision. They're just bouncing off of each other. We're not losing any of that kinetic energy.
Yep.
But let's say we deal with an inelastic collision. Remember, in an inelastic collision, in this case, let's say it's completely inelastic, these two carts are going to come connected to each other when they collide.
Yeah, they're not going to bounce away.
And this formula, conservation of kinetic energy, is useless to us. It doesn't help us at all. But what's neat is since they have a shared velocity after they collide, we can use the conservation of linear momentum to figure out, where's that energy going. And so,
yeah. I mean, you've seen, let's say, like a car that drives into a tree and it wraps itself around a tree.
Yeah.
Yeah. Practically what's going to happen here.
If we write it out like this.
Sorry?
I was going to say, to take it, explosion is when the collision can't contain that energy. That would be explosion, wouldn't it?
Mm-hmm.
Is that
would be momentum.
Okay.
Yeah.
Get to it.
Momentum before and then momentum after. You can see that in this case, those two carts are going to become connected. And so the velocity of both of them after is going to be exactly the same. They're going to become connected. And so I've written that as V3. This is our new shared velocity of the two. And so what I can do is...
Yeah, because they intertwine to each other and makes a singular momentum because they're together.
I can plug in my values. We had a 1 kilogram cart going at 5 meters per second before the collision, and a 2 kilogram cart going at 2 meters per second after. The masses don't change, and so I can solve for that V3. I can solve for a velocity of 3 meters per second. And so if it's an inelastic collision, since they're connected, that shared velocity allows me to solve for the change in linear momentum. Let's make sure that that works. Yep, they both have 3 meters per second that's going to the right.
Very simple to stuff. Yeah, Brainstein, no, it's more than 3 globies, believe me. A lot of the globies watch and don't actually comment. And then you get the brave keyboard warrior trolls that come in afterwards and then just comment constantly. Showing stupid stuff like, microwaves don't cook food. I actually had someone today telling me that if they cook a chicken in the microwave, it doesn't burn their hands when they take it out. It's not heat. It's not heat. Microwaves don't cause heat, people, because they don't understand. They don't understand radiation is still heat.
Yeah. But I suppose all them electrons are not letting it get to your hands either. It's absorbing the heat. Just like that knife that doesn't cut you.
Yeah. Oh, it's crazy.
No.
But it's good to have everybody here. Obviously, we only got another half an hour and then the stream's going to be up, so... Is there anybody in chat that wants to come and talk? You guys are more than welcome to come in. Yippee! Mike, PJ, would you be able to maybe stick the link in for the people?
Oh, yeah, sorry. Yeah, absolutely. No problem.
Sure, thanks, man. I have nothing to say. Can you believe it? What's going on?
What's going on?
Well, I almost reviewed the presentation from Jaron today about his why science doesn't prove things, because he did an actual presentation. But I think I was a bit sick of Jaron's EDSC for a week. There's only so much you can do. But we can talk a bit about Mr. Sensible's chat if you guys want to.
Yeah, why not? Hey, at least he was civil the other day. I mean, out of them all, he is one of the more civil ones. I mean, he can sometimes be a little bit take the piss and that, but at least he was damn friendly.
Yeah. Yeah, no, he's always very cordial. At least he's just not very sharp though. He doesn't realize when he says stuff, he literally debunks his own arguments. But yeah, I mean, like today I released that little short snippet where he was trying to explain pictures of a galaxy with a star. It's it's science. I see a picture, therefore science.
Yeah,
and then
Einstein's.
yeah, I mean, it's so dumb. I mean, okay, I can predict it will happen, and the cause would be God sticking a magnifying glass, and that's why we see what we see. Oh, look, a photo. Therefore, I've proven my cause. God stuck a magnifying glass in front of there. This is how idiotic it is. That's why it's not science. They don't understand you have to manipulate the independent variable to figure out if that's the cause. And what's the first step of the scientific method? That would be observation.
Observation, yeah.
So if you make a prediction before observation, it's not scientific. I mean, many people have made predictions about sports teams winning the World Cup. Was that scientific?
Certainly not.
No, exactly.
That's fluke.
It's fluke, exactly. It's crazy. He says, Jim Smith, radiation isn't heat. Radiation can create heat. No shit, Sherlock. It causes the molecules to move around faster. It heats up. So in other words, the food inside the microwave, what caused it to get baked or cooked? Heat. The cause of things cooking, heat. What did the microwave do? Induce heat.
Well,
Thermal energy.
Some people think it's the duration of time you wait that causes it to cook.
Guys, we're wasting our money buying electricity. We can just stick a pot of water on the stove, don't need to switch it on. If we just wait long enough, it'll boil. If we stick a thing in a microwave, don't need to stick it on. The chicken will just cook on its own, guys.
I'll remember that later.
I mean,
solved everything.
Yeah, it was solved. I'm sure Vicky's on for that as well. Imagine you just stick a roast in the oven, you walk away, go shopping, come back, and it's just cooked.
It's amazing.
Eh?
How did nobody know sooner?
Oh, but don't forget, with Mr. Sensible, he says it goes on if you actually look at it or not. So as soon as you look at it, it will be cooked. But if you didn't look at it, it didn't get cooked.
No.
Magic.
Weird. It's weird because I'm sure they say a watch kettle never boils, not a watch kettle boils. Wow.
He says, why isn't the glass turntable getting hot? Because it has a different conductivity than the chicken, you bloody... Just like a pot, sticking it in an oven. Why is the water not boiling inside the pot? Would that be because the pot itself, the plate, is conducting all the heat to itself to heat up the pot's base? Yeah, it's the same in a microwave. Everything's being concentrated to the object, not the plate. And by the way, if you leave it long enough, that glass plate will also get hot.
It does.
Stand and watch.
Yeah. That's it.
I can guarantee you, stick nothing in the microwave and just stick it on. That glass plate will get hot quite quickly.
Yeah. Well.
Why waste electric? Just stand and look at it.
Yeah, that's it.
Exactly. Something with zero moisture would get hot, right? Wouldn't get hot. Why? What has moisture got to do with something getting hot or not?
Yeah.
It would just, if something got moisture, it's just going to take longer to heat up, and when that moisture starts heating up, it will start evaporating and get dry. That's all. Vegemite on a cup, what? And tea.
It's what Taylor Vision wrote. Speed up time.
Yeah, just speed up time, guys. Time is an independent variable, apparently.
Yeah, absolutely. Manipulated just by waiting.
So I want something to show me what time has ever caused. Has anybody even observed anything that time has caused?
No.
My beard to go grey.
No, that's entropy, mate. It's the keratin. I think that's the keratin in your beard that's giving in.
Wisdom. Wisdom around.
Yeah. Jonathan Clark, pick up a hot pan with a wet cloth. You're definitely wrong on that one. Okay, hold that hot plate with the wet cloth long enough. The water warms up with the hot cloth, and eventually your hands will burn, and that will get dry. It will evaporate. Jonathan, you're talking to someone that wanted to become a chef at a stage. I've burnt myself quite a few times using wet cloths taking hot things out of ovens. Yeah, I've got actually an oven mitt here that's burnt to a crisp because because of an oven. So yeah. Time causes my clock to tick. No, that would be the battery. Take the battery out, it wouldn't. We don't know what time is exactly, Blue Pill. It's just a concept. It's a concept that man made so you can reference the duration. That's all. It just makes life easier to understand. I mean, imagine we didn't have the concept of time. How would you know to come on my stream? Because there wouldn't be any time for it. It would just be random.
It would just appear.
It would just appear. Oh, look who's here. And there wouldn't be any days. There wouldn't be anything. It would just literally be chaos, I guess.
Yeah.
Thomas Larson. Live in the moment heals the soul. Everything happens in the moment. Everything else is an illusion. Ooh. Philosophical on us.
Have we finished the thermodynamics lecture then? Can we go play now, sir?
Yeah,
You can have recess now.
Yeah, you can go play. I'm sure Barbie and Ken are waiting for you. So let's see what the votes say. We got 65 votes, law of entropy. The first law is 15%. I don't know who clicked on that. Second law, 71%. Yay, we got 71% of people that actually know it's the law of entropy. Third law, 5%. Fourth law, 9%. So yeah,
I think some people were just clicking some of the other ones.
Yeah. So if we let's take the 0th law, guys, that's the 4th law, and you stick let's heat up a ball bearing, and we stick it next to another ball bearing that's not heated up, and they next to each other, and they're just touching one another. What's going to happen?
Heat transfer.
Yeah, exactly. But what's going to happen to the hot ball?
It'll equalize to the same heat as the other ball.
Yay!
Cool.
PJ.
Oh, yeah.
There we go. Exactly. Yeah, it will equalize. So the hot ball will cool down and the cool ball will heat up until they are the same temperature. And eventually they both will cool down to an equalized temperature, to room temperature, as everything will disperse into the surrounding system.
Yeah.
Jonathan Clark, how can you train to be a chef and not understand how time affects things? Time duration is a control. It's not a cause. It's not an IV, Jonathan. If you make a souffle, if you don't add the ingredients and you just wait there, it won't do anything. If I go and try and bake a cake and I stick it in an oven without putting it on and I wait, nothing will ever happen, because I can wait a minute or I can wait an hour. It will have exactly the same effect, Jonathan, because what causes a cake to bake? Heat energy.
Right.
No, time baked your cake.
I don't understand how we have to actually explain this to grown-ass people.
No, I couldn't believe it when I first heard it. Like, come on.
And I mean, it's not just one or two people. It's like a crazy amount of people.
It is.
Jonathan Clark, what happens if you bake it for 1 second? And then it's not fully baked. That's just retarded.
Just not much.
That's just retarded. How about you take that cake and throw it in a volcano? It'll instantly get cooked to smithereens, correct? Because it's too hot. Yeah. What did we change? Heat. Flat enough. Time causes impatience.
I think you say impotent.
Nice.
PJ's pictures swatty Swatkins. Never been called a swat before.
Exactly, Paula. Experiment. IV, controllable cause. Causes DV effect under the condition of CV condition. Null if disapproved. Exactly. So you need time to be it. No. Time is always there. You can't stop time. You can't forward time. You can't reverse time. It's duration. It's a man-made concept. It's just literally giving a timeline so you can have order. That's all it is. If I go and bake an egg, for me 9 minutes is perfect. For someone else 7 minutes is perfect. For someone else 10 minutes is perfect. But if you don't give the right amount of heat, you won't get the result. The time is irrelevant. The time is literally just the control. So you know, okay, I've made the water boil 100 degrees Celsius and I've left it to boil for 9 minutes. To me, that's a perfect egg. Did the 9 minutes boil the egg, or was it the heat that boiled the egg? How do we know to find out which caused what? Okay, let's do the same by not boiling the water. Put the egg in the water and wait 9 minutes. I guarantee you, when you take the egg out, you crack it open, it would be raw. Okay? What causes it to boil? Heat. Hey, Richard Bull.
He's fine.
It's crazy. But that's what I try to ask Mr. Sensible as well. Because he says space-time bending. I'm like, okay. How do you bend nothing?
Yeah.
They said, oh, the fabric. I'm like,
fabric. What fabric?
What fabric? How do you bend how do you have a fabric that's nothing? Space is just availability. That's all space is.
Mm-hmm. Yeah. Time is the IV, then it's the cause of everything.
I watched an interesting thing a few months back. A guy cooked a chicken by just slapping it.
He plucked the chicken by slapping it?
No, cooked a chicken.
Oh, cooked it. I thought he said plucked it.
He built a machine that made like a hand kind of thing, and he slapped the chicken.
It makes sense.
Until it actually cooked, because it was transferring the heat energy until the chicken eventually cooked.
Wow.
Obviously, the first few tries he did wasn't very successful. It just literally slapped the chicken into pieces. But eventually, he got it right. That it slapped. I wonder if we can find it. This is actually quite good.
Wow.
Because think about it, it's the same when you take a hammer. There we go, chicken slap.
Wow. Cool. Uh-huh.
There you go. I cooked the chicken by slapping it. Check there. So you made a
perpetual slapper.
Yeah. I mean, it's the same as you take a hammer and you hit a nail enough. Yeah. It gets hot because you're transferring the chicken. Look, Gordon Ramsay reacts to cooking chicken. Okay, that should be good.
Trying to cook chicken by slapping it, part 1. So there's this meme that says you can cook chicken if you slap it fast and hard enough, but I can't slap that fast and hard,
need to be roasted.
so I built this robot to slap it way faster than any person can.
What the hell? This is TikTok, right? Not Pornhub.com. You have to be kidding me. Honestly. What a freaking donut.
So we let it run, and it got worse.
Slapping your meat like that. You should be ashamed, young man. Honestly. What would your parents say?
Probably really tender.
Well, it worked. It worked.
That's crazy.
Slapping a chicken.
That was quite calm for Gordon Ramsay.
Kitchen of the future. You walk to the back, you just see a whole bunch of chicken slapping machines. A gerund slapper, retroball.
Yeah.
Sometimes I feel like slapping him to wake up.
Yeah, we'd love to cook Gerund.
Bryson, how do you bend space-time? With mass equivalent of energy. Very simple. Space is availability. That means there's nothing there. Okay? It's something that's just available to get filled. Time is, again, just a man-made concept. Duration, to give you, on a timeline, some kind of order. You can't bend any of them because they're not physical. There's nothing physical about space or time to bend or manipulate. They don't exist. You get it? Oh. Yeah, I don't think they know what is mass, by the way, guys. Space is over.
The amount of stuff in a thing.
Yeah, I would say the best way to explain it is just stuff.
Stuff, yeah.
Stuff crammed. Stuff crammed into an object. Hey, Lumpy, good to see you, mate. Coming when we're going to close off. But it was a good show, though, guys. I enjoyed it. Yeah, because next Wednesday is the McToon debate on celestial navigation. So I'm actually looking forward to that. Yeah, I'm looking forward to it.
Him and his mate, Jaren, will probably have the same.
Yeah, I already warned McToon. I said I'm not Jaren.
Yeah, exactly.
And I heard McToon referenced me on his Iggy debate today.
Right.
Apparently talking about me. I don't know what he said though, so that'll be interesting. Yeah, McToon is a bottom feeder.
Oh, he's below that.
The guy, I don't know. McToon loves playing with Lego, and he's very obsessed with space, and claims to be a Christian while trying to discredit the Bible. Makes so much sense.
And I don't understand that we can be a Christian whilst discrediting the Bible, since that's how we know what Christ is like.
Yeah, it's really weird.
Hey, don't diss Lego. I grew up on that stuff.
Well, he has streams where he literally goes and builds Lego ISSs and.
I didn't know that. He actually does that.
Yeah, he has streams on that, and they got like 600 people watching him build Lego and drooling over his Lego playset. Like, what the hell's wrong with you people?
Wow, it's like sitting watching someone do a Rubik's Cube or something.
Ferris Furfer said he actually complimented me. Wow, that's insane. Do you have a timestamp? No, Brian said nobody said mass does not exist. The definition of mass does not really exist because there's more than one definition. You guys can't decide what mass is. Heck, inertia has the same definition. Yeah, ballers think the only ones who attend university. That's very sad, though. Let's take Jesus Freak Computer Geek, for instance, guys. He worked at NASA for years.
Yeah.
And he literally tells everyone straight out, they never went to the moon. It's fake. Space travel is fake. He says it straight out. He worked for NASA. He did very important work for them. What do I do in my spare time? Play with my kids. Spend time with my wife. Do house
with his kids.
Yeah, play house chores and scream at my children for being naughty. Do mechanical work. Spray. I used to do a lot of airbrushing. But those were the days when I had more time. These days I find you don't really have time for anything anymore. It's really crazy. Just not enough time in a day for anything.
I know. I've been meaning to go fishing for ages, and I just haven't done it.
Yeah.
I need to go again.
My child actually asked me, because he got an old fish tank in the garage the other day. He's like, "So when are we going to get fish again?"
I've got a fish tank lying empty there as well. I'm thinking the same thing.
Hobbies. Well, At the moment, my hobby is YouTube. I really do enjoy YouTube, to be honest. It's a lot of work, but I do enjoy it. But yeah, airbrushing's another hobby. I like painting. I like drawing. I did study art. I like doing ceramics. And obviously working on cars. I'm planning December to be doing the Corsa totally over. So I'll probably do a whole series on that because I'm going to have my son helping me. So I'm going to do it from the ground up. Stripping everything out, doing the bodywork completely, trying to get a new engine and gearbox, sticking it in. So looking forward to that. Because December we close at work, so at least I'll have time for that.
Yeah, Ian Molyneux watches Flatzoid videos in his spare time. That's his hobby.
Wow, that's awesome.
Oh, nice one, Lumpy. He's got a bunch of fish, he was saying. Nice. Bass, was it?
Retro Bull, news alert, India lands on moon. What?
Yeah, what a joke.
Like recently when that one probe supposedly crashed into the asteroid or moon or whatever, and it was like, you see, space is real, and you're like, no, they just got rid of the evidence because it isn't real. That's it. Yeah, Jolly Man, inertia is resistance to motion. Exactly. That's what they say is mass. Resistance to motion. They can't decide what's what. Yeah, the Indian landing cartoons are crazy. It's very bad. Playing with cars, not much different than playing with Lego. No, playing with cars is grown-ass stuff. Playing with Lego is children's stuff. I used to play with Lego when I was small. I think it's very different by trying to, let's say, hone an engine than put two blocks together to build a Empire Strikes Back figurine. I think it's two very different things. I can use that engine to drive around. What am I going to do when I build that figurine? Oh, it's going to sit in my background. Unless I play with it.
You can stare at it.
6:25 is that timestamp for that.
6:25. Let's see if we can find it in McToon. McToon Live, I think. This should be interesting. I want to see what he said. I think I said it was in this one. 16 hours ago.
This is how to get fit.
Oh, yeah, how to get fit. Just eat right. Don't exercise. Yeah, whatever, dude. 6:25. We'll start at 6:14.
It's more French than me. Let's see. Oh no, it's Andy says, look at Pete MK as he just debated Flatzoid and celestial navigation. Sounds interesting. The one thing I do have to say about Flatzoid is he can get completely, I'm just demolished. Just
what? Is this supposed to be a what? You said
squished flat, like the squished flat, right? Like the Monty Python foot coming down and just stomping on him. He can get that flattened, and then come out declaring that he did well. It's you've got to admire the positivity that he has.
But
wow.
Pure projection from McToon.
Thank you, Furious.
It's almost like he's trying to get a pre-reaction out of you before the debate.
Well, this is my pre-reaction. Wow.
The way he started, I actually thought he was going to compliment you.
Well, I did say it was a compliment.
Yeah.
So this is my reply. Tell me where I got completely flattened, please. Show it to me. Wow. Because what's the thing that usually happens when I debate someone? I get them to validate my argument. Yeah. I lead them to validate my argument. That's my whole MO in a debate. So I don't know what he's talking about. Sandy's Banana. India, first to land on the moon's south pole, debunks flat earth. Oh, wow. The moon has a south pole now? Okay. Well, guys, I guess I'm going to have to go switch the generator off.
Oh yeah.
So the stream is finished then.
It is kaputted.
So what is your guys' thoughts on the stream?
My thoughts is I'm gutted about my new computer.
I hope you get it sorted.
Yeah, I think it's maybe the, I don't know nothing about RAM and all that, but I think by resetting it's probably the amount of RAM and all that in it. So, yeah, we just got to have to look for something better, put it back and put it towards something better. I think. Yeah. But as for the stream, yeah, good stream as usual. The bits of it I did see when I wasn't trying to get the computer all back up and running. Yeah, I liked it. I liked that video we showed the guy who laid it out in layman's terms about when he was talking about the elastic collisions and inelastic. And
that Indian guy.
That was really good. I like that. Like that. He does put it in a way that is really understandable.
Yeah.
So yeah.
I just want to say, Brainstein, well, I think it was Brainstein says, we can see the kind of things that Flat has been watching. Yeah, I love watching buff dudes, dude. I used to actually do some bodybuilding when I was younger. I used to enjoy gymming. So it's not something that I don't understand what's the problem. Buff Dudes rocks, by the way. I don't know if you guys watched Buff Dudes before.
No, I used to like going to the gym, but it's been a while since I went. I need to get back.
Yeah, no, now that I'm married and stuff, I don't need to worry about my body. Come on, I got a dad bod now. I got a six-pack, you know.
In the fridge.
In the fridge. So yeah, but yeah, Jeff, you got any closing statements?
No, I think I'm okay.
But
yeah, it was a great stream.
Yeah, I think it was a cool stream. But yeah, I want to say thanks for everybody for coming. Really, really appreciate it. Please do hit the likes, share the show if you haven't already. It does help to get the show out to further audience. And I appreciate all the support. You guys are really, really awesome. I'm actually in the mood for some Christian Flat Earth content again, if you guys want. If you find any you want us to review.
That'd be good. I'll look for something like that.
Because I haven't done it in a while. I still do search now and then, but it's difficult to find fresh content on that.
Of course. I'm a little gutted because I actually thought Mick Toon was going to give you a compliment.
It was a compliment. He was projecting his insecurities onto me.
Well, that's true. Well, yeah, that's absolutely brilliant compliment.
So we'll see if Professor Fulbal will be able to rebut my presentation, though.
Probably not.
I doubt it very much.
No, probably not. But yeah, thanks all for coming. Really appreciate it. Tomorrow night, if you guys have any video that you want to review, just email me at Flatzoid. What the hell? At flatzoid@gmail.com, guys. Thank you all for coming. I'll see you guys all tomorrow night. Many, many blessings. May the pressure be with you.